Okay, so so far we understood the SoC blocks, why high performance matters, what it brings to us in our real life use cases, and why how important it is to reduce the power dissipation in those devices. And we got a good picture of how there are different blocks of operations in the SoC, CPU, and say multimedia, or if it is a mobile, then it's there is a modem, or many other blocks. Okay. Now in this chapter we are gonna discuss about the CMOS technology and the design architecture of SoC to reduce the dynamic power. Okay, so let's move quickly. So so very first let's have a look on this curve. This is a VF curve. So this is a VF curve of any switching circuit in the silicon. Okay, so suppose let's say there is a CPU, and a typical VF curve will be like this, in which the basic fundamental that I'm trying to explain, that in order to achieve the higher frequency we need to apply the higher voltage. Okay, and as this frequency increases further, this increase for a given amount of increase in the frequency required, the more and more voltage increase will be required as for the higher frequencies. So this is one fundamental that we need to keep in mind, that V and F are related. Now let's put our focus on the dynamic power, that is CV square F, where V and F are related. Okay, so as the V is the function of like V square, so if we reduce the F, say for a required operation or required throughput, right, and we are able to reduce the frequency somehow, then we get multifold advantage on the V, because V will also reduce. Okay, so so we will take the advantage of this factor. Actually, in the coming slide we will see that how we are gonna do this. Okay, before going there, one aspect we want to discuss is technology node scaling. And in the technology node scaling, a transistor's gate length or channel length that gets reduced, and we can see that a couple of years before we were at 2 nanometers, now it is 10, then 7, then 5 nanometers gate length. Okay, so with this, what comes as an effect? As an effect of this technology node scaling, for the same performance lower VDD is required. So with this scaling, technology node scaling, we get, for the same performance we have reduced dynamic power, CV square F, VDD is reducing, right? And also there's a fact, there's a interconnect which basically pose as a capacitance. Those capacitances are also reducing. So we are getting multi-fold benefit. So this is all win-win. So, and as we reduce that the channel length, and as we scale the technology, many benefits we are getting. In fact, the capacitance is also reducing. For the same frequency of operation, because circuit is becoming faster, we need to apply the lower supply voltage. So C is reducing, V is reducing for the given performance. My dynamic power is reducing drastically, and at the same time, because the channel length is reducing, we are able to fit more transistors in the same silicon area. So that's why I said win-win situation. We are getting all the advantages only, right? So dynamic power is getting reduced, more transistors are being fit in the same area, and that reduction is also multifold, because there is net effect on the VDD that is getting reduced, with that is V square in dynamic power, and capacitance also reduces actually. Okay, In this figure, we just wanted to show that if this is an N7 technology and this is N5 technology, for same amount of power, we get more speed. Okay, so just a depiction of the fact that we discussed. Okay. One more concept, that is about the transistor size. So when we are discussing the technology node scaling, that scaling is happening only in the gate length. Like in this is source, this is a drain, and there is gate in between. The gate which is reducing is this gate length, but there is factor of width also, okay, for a transistor. That is why even with the scale technology, we can have define a transistor size. What is my transistor size? This width, okay. So as the size of the transistor tends to increase, the delay, the circuit delay for that transistor, that decreases. So bigger the transistor, smaller the delay, means faster the circuit. And we want to take advantage of this. How? Suppose there is some critical path where there are more number of transistors compared to other path. What we do in those cases, that we increase the transistor size. So when we increase the transistor size, what happens? Those delays becomes less and less. First of all, it is able to compete with other path. So that serves our purpose. Otherwise, what will happen? While data is supposed to reach at the same point of time, this will take more time because there are more gates in between, and delay will be more. So we optimize in such case that we put faster gates by the increased size, transistor size. But we take advantage in the power as well for this fact of like bigger transistor size gives lesser delay and faster circuit. What we do, we upsize the transistors, and while we upsize, the basically performance gets boosted, and with that faster circuit we are allowed to scale down the supply voltage to equalize with the original delay. Okay, so we got the same performance at the lesser voltage supply, and thus we are able to decrease the switching power, but at the cost of area because the transistors are bigger. Okay. Now we come to the fact that we initially discussed about V and F operation. If we are able to reduce the frequency, we get multifold decrease, because V is the term V square. Okay, and we decrease the frequency, the V is decreased, but power is the term of V square. So we get multifold saving in the power. That's why the concept comes of area and power trade-off. Okay, so suppose there is one unit which is doing certain operation of ALU for me, and this runs at certain F value. I can replace it with two units which run at half that frequency, and obviously voltage will also be reduced, not exactly V by 2 because curve is not linear, but again with two units at F by 2 I am getting the same performance, but voltage is less, and that is the factor of V square in the power dissipation. So I get the same throughput out of this circuit because this is F by 2 but 2 units, but my voltage has reduced, and that gives me a benefit in the overall power dissipation. So this concept is called area for power trade-off, and this is applied in multiple ways in silicon fabrication. Here we want to depict the parallelism for performance. Okay, so the concept is quite similar what we discussed earlier, that instead of running one execution unit or one piece of unit which processes for you at higher frequency, it is advantageous to run multiple units at lesser frequency. Ultimately that's what we are doing. Okay, there are many other advantages that do come with this that we will discuss, but primarily in the sense of power, Rather than running one array of execution units at very high frequency, it is advantageous if we are using 8 sets of same block at the lesser frequency. Okay. There will be other advantages in which a process is broken into threads, and those threads are running parallelly on each other, giving the performance advantages and efficient uses of the these processing units, because one which is not being used can be turned off and it gives those granularities, but that we will discuss in coming sections. Right now our focus is that running at lesser frequency and trading area for power. So we can rather than running at high frequency, we will like to run at lower frequency in multiple parallel units. We multiply those units, operational units. One more example is of CPU pipeline. So let's assume there is 5 stages of operations for one full operation that is needed, one instruction, let's say, that runs in 5 stages of operation, and every stage, let's say it is 1 clock cycle. Okay, so in order to execute that one instruction, that will take 5 clock cycle. We do take advantage of parallelism here. Okay, we start executing 5 instructions parallelly. There will be issues of interdependence of each other that we will need to take care that which one is executing first and its data is affecting the next one. So those hazards, those are a topic of hazards that we need to discuss separately. But here what we want to understand, that using this parallelism, there will be net effect that each instruction is executed in 1 clock cycle rather than 5 clock cycles, because 5 are being executed simultaneously one after another, and the net effect will be in one clock cycle we are executing one instruction. So this is a technique we are using for improving my performance. Just I gave her some terms like MIPS, million instructions per second. This is how in the industry we denote the performance terms for the CPU or GPU. Like in GPU there are teraflops, the flop is right, floating point operations per second. So let's assume these are, every small square is an execution unit, and these are arrays of execution unit. So how many operations are happening. So these are terms in which we measure the performance, and these are the techniques through which we enhance the performance of the circuit for the given technology node, and by techniques of architecture, SoC architecture. Yeah. Again, similar concept. Suppose one CPU is running at 2 gigahertz, and let's say I have 4 CPUs here which are running at, let's say, 500 megahertz, so that it equate 4 CPUs at 500 megahertz and one CPU at 2 gigahertz, and net effect of performance is same, but in this case the supply voltage will be less. And let's take a case where the CPU bandwidth is fully utilized here and here, then this will be giving the same performance but at lower dynamic or switching power, because the applied voltage becomes less, it is operating at lesser frequency. Okay. There are some additional advantages that come with this architecture, but here I wanted to depict this concept of lowering the voltage by deploying multiple units of operating at lesser frequency. Okay. There will be other advantages, because here the granularity increases and operating system can take advantage of shutting down other CPU cores while there is not enough workload and only using one core, right? So those advantages also will be here. Okay, this is one topic of big little architecture. In this, what we do, This is primarily for saving power. One of the architecture which is used for CPU in CPU cores in mobile or CPUs, even in the PCs or laptops. So what happens here? There are two clusters of the cores. In this case, let's say there are two clusters of 4 cores each, and one cluster is called little and another cluster is called big. So the concept is that little is optimized for those workloads which need lower performance, which operate at lesser frequency, but this is more power efficient cluster. So though it is operating at a lower frequency and it is usually on for most of the time, and it is more power efficient, okay, for low frequency or low performance throughput requirements. And the other cluster is designed in such a way that it is optimized for high frequency workload, okay. So in the VF curve, what we saw earlier, as we increase the frequency, the more voltage is applied. So in this case, what we do, this is the big cluster is optimized for higher frequency, okay. In general, what happens, if you, for the same core, if you keep increasing the frequency, it will not be power efficient in high frequency domain, high frequency region, because of the VF curve and very high significantly more voltage increase will be required here, okay. So the technique is like that. One CPU core is optimized for more power efficient operation, which is on at the most of the time, but its performance is less. It is used for tasks which are not consuming too much of CPU power. When there are tasks which actually require CPU throughput and high frequency of operation, there is another cluster which is optimized for the high frequency operation, okay. But it will not be efficient to use for this kind of workloads which are not utilizing it fully. If I keep it on for those workloads which need lesser CPU throughput, it will actually be more inefficient, power inefficient. So it is useful for when it is used fully for its capacity for high frequency operations, okay. So this there will be a implementation in CMOS technology, how transistors are fabricated, as well as the architecture, right? With that we will see a little bit in order to make it optimized for high frequency operation, okay. You already understood the concept of bigger site transistors, and then there are some architectural changes. So that is one concept that comes handy for saving overall power. Now operating systems are very smart. They understand the hardware, okay. They know how to make good use of the hardware available, okay. We will see that as well. So while I was telling the big versus little, so there is change in the architecture itself, right? This is ARM A15 and ARM A7 used as a big and little, and that is out of order, high performance, high throughput pipeline, right? And this is in order, and there are less stages in this pipeline. There are more stages in that pipeline, and that suit for that operation which is requires higher throughput, okay. Here it is just depicting the same fact as I discussed, some applications which need very less amount of processing power. So at that point of time, mostly we are using the little core, and when there are performance hungry applications, right, videos, high definition and displays, etc., then we turn on the other cluster cores in the other cluster. Yeah. And as I was mentioning, the CPUs, which are very smart, they understand the hardware the operating systems, right, that understand the hardware beneath them very well and make use of them. So there were techniques how this big little is being used by operating system, and from top to bottom, very first is like cluster migration. That is nothing but the one of the cluster is completely off and the other is completely on. While suppose workload is running on little, and the performance the threads which are running, and there is performance requirements that needs more higher frequency and then operation, then the workload switches completely from low little cluster to big cluster, and it is less efficient because in that case just if on one core if a thread is running and it needs more performance, and the entire cluster switches and end up dissipating more power because it is less power efficient, the big cluster. Okay, then the next technique is better than the previous one, where what we do, we make, rather than switching the clusters itself, right, we are pairing the cores inside big and little. So but the limitation here is that if there are 4 cores in the little, we need to have 4 cores in the big so that there can be pairing can be done. Okay, so now operating system operates on those pairs. So one thread is running, it can be turning on one of the CPU core in that pair. Okay, and the rest can remain turned off. Okay, suppose 3 cores in the big are off and 3 cores in the little are off, and only one pair is active. In that pair also one of the core will be active at the time, other will be off. If there is more threads, they can run on other 3 pairs. So at the pair level one of the core can be off and on. But the limitation is that in this case we need to have the same amount of cores in big and little. This problem is solved in the heterogeneous multitasking. There is no such need now. Now any core in the little can work with any core in the big, and thus energy aware scheduling threads of operating system can choose which core in the big and which core in little they need to operate on, and there is no such pairing, hard pairing of cores. So okay, so far we discussed like area for power mostly and parallelism for performance. Another technique is that in some way we can reduce the switching itself, right, the switching activity itself. So one of the activity is gray coding. As you know that sequential data in the gray code changes only 1 bit at a time. So mostly like addresses of instructions which are sequential in nature, we will use gray code. So from sequential data, from as it proceeds, only one of the bit in the entire bus changes, and thus the overall switching will reduce. Similar technique is like bit inversion, in which if there is, suppose there is a bus and there is data transmission is happening, say 32-bit bus, and one set of data transmitted, the next set of data comes. In this next set of data we can decide if we invert the entire bus from 0 to 1, all the bits in that, is it closer to previous data? If it is closer, then at the receiver end less transitions are happening, and that's saving the power. That is one of the concept that was deployed in DDR, in some of the DDR version, I think DDR4. So that's bus inversion is also one of the thing we do to reduce the switching activity. Okay, so switching activity reduction is one of the architecture technique. Yeah, okay, so we'll take a pause here. Okay, in the next chapter we will discuss about techniques to reduce the leakage power and from the both aspects, the CMOS technology as well as design and SoC design and architecture.